This is part 2 of our mini course on deposition processes in semiconductor industry. Deposition processes form a fundamental pillar of semiconductor manufacturing. These techniques involve the precise placement of thin films onto a substrate, enabling the creation of the intricate structures found in modern microchips. In manufacturing, deposition is considered a core fabrication process, crucial for constructing transistors, interconnects, and insulating layers. Without reliable deposition methods, advanced integrated circuits would be impossible to build. The resulting thin films are often just a few nanometers thick, but they must be uniform, defect-free, and adhere perfectly to the underlying surfaces. Precision at the atomic level is essential to meet the performance demands of today's semiconductor devices. From a technology perspective, two dominant categories are physical vapor deposition, or PVD, and chemical vapor deposition, or CVD. These technologies offer different advantages in terms of film composition, conformality, and scalability. Together, they support the diverse material and structural requirements of the semiconductor industry. Applications and examples. Deposition technologies are crucial across a wide array of applications. In the Internet of Things, or IoT devices, atomic level control enables precise manufacturing of temperature sensors, RF communication chips, power management ICs, and ultra-low power microcontrollers. These components help create smart, connected products that run efficiently on minimal energy. In medical devices, the stakes are even higher. Pacemakers, glucose sensors, cochlear implants, and neural interfaces all rely on reliable, high-performance semiconductors. These systems often require biocompatible coatings to operate safely within the human body over long periods. Emerging applications are also driving innovation. Quantum computing uses superconducting qubits, while AR/VR displays leverage micro-LED and OLED technologies. Edge AI benefits from ultra-low power chips optimized for decentralized computing. In space electronics, radiation-hardened chips are vital. Across mobile, computing, automotive, and industrial sectors, deposition is truly everywhere. Enabling more than 5 billion mobile devices, every processor, over 100 chips per car, and smart manufacturing processes. Summary and future. Deposition is often referred to as thin film magic for good reason. At the atomic level, it constructs the invisible yet essential layers that drive the digital world around us. This includes transistors, memory, sensors, and more. Two major approaches dominate. Physical vapor deposition, or PVD, is used primarily for metals and excels in speed, while chemical vapor deposition, or CVD, is preferred for insulators due to its better step coverage. Looking forward, atomic layer deposition, or ALD, is taking center stage with angstrom-level precision needed for nodes at 3 nanometers and beyond. AI-driven process control is transforming manufacturing by using machine learning to optimize deposition parameters in real time. Green manufacturing is another vital trend, emphasizing sustainable materials and energy-efficient processes. Why does all this matter? Because deposition is the foundation of innovation and serves as an economic driver, supporting trillion-dollar industries and millions of jobs worldwide. Summary and future, Part 2. Understanding when to choose a deposition method is critical. Use physical vapor deposition, or PVD, when metal layers are needed, especially for applications requiring low processing temperatures and fast deposition rates. It's a go-to choice for speed and simplicity. On the other hand, chemical vapor deposition, or CVD, is preferred when working with insulating films, complex 3D device structures, or when excellent step coverage is crucial. The technology roadmap shows us where the industry is headed. From 2024 to 2025, mass production dominates. Between 2026 and 2028, development efforts will focus on fine-tuning new processes and materials. Beyond 2030, the target shifts toward 1 nanometer features and breakthrough materials. This aligns with the broader innovation cycle, beginning with research into new materials and processes, followed by development to optimize performance, and culminating in high-volume production. This cycle fuels continuous innovation and opens the door to next-generation applications. Summary and Future, Part 3. The global impact of deposition technologies is truly staggering. Every year, over 50 billion devices are produced, supporting an industry valued at more than $500 billion. This growth is fueled by emerging applications like quantum computing, which relies on ultra-sensitive superconducting qubits, and AR/VR displays that use advanced micro-LED and OLED technologies. Space electronics demand radiation-hardened components, while biosensors continue to advance diagnostics and health monitoring. To stay competitive and relevant in this rapidly evolving landscape, future professionals must build skills in key areas. These include materials science for understanding atomic interactions, process engineering for system-level design, data analytics and machine learning for intelligent process control, and sustainability to ensure responsible manufacturing. Getting involved starts with studying STEM fields, participating in research, exploring careers in the semiconductor industry, and contributing to innovation. Together, these efforts will power the next generation of devices and applications shaping our world. Deposition. Building tomorrow's technology. Deposition stands at the heart of building tomorrow's technology, serving as the invisible foundation of our connected world. At its core is precision, atomic-level control that allows for the creation of ultra-thin layers just a few atoms thick. This capability enables the miniaturization and performance required in today's semiconductor devices. Innovation thrives on this precision. From high-performance processors to advanced sensors and quantum chips, deposition technologies drive breakthroughs across industries. The impact is global. Deposition supports transformation in healthcare, communications, automotive, computing, aerospace, and more, touching nearly every aspect of modern life. Looking ahead, the future is filled with unlimited potential. As we push towards smaller nodes, greener processes, and smarter systems, deposition will remain a key enabler of progress. Whether it's powering next-generation AI or unlocking new realms of computing, deposition technologies are building the path forward, one atomic layer at a time.